Okay, so what I've put together is a Year 11 differentiation test. It's got 5 multiple choice questions, followed by 5 short answer questions. The multiple choice we're going to do without a calculator. Unfortunately, the formatting hasn't come out great, but we can see with this first question here, it says f of x equals 2 equals x to the power of 2/3, and g of x equals e to the x. Okay, and then the question is, what is f of g of x? Well, f of g of x, so we take the function f of x, and wherever we see an x, we plug in the function g of x. So that's going to be, well, there's an x here, so that needs to become e to the power of x to the power of 2/3. Okay, hopefully now we can simplify it down, and we can use our index laws. That's going to give us e to the power of 2x on 3. If we write that as some sort of root function, we can see that it's the cube root. The denominator is always the nth root divided by e, and then we've got this still in here, so e to the power of 2x. So it's going to be c here. Yeah, I can see that these ones are a bit tricky to read, but hopefully you can see that it's the cube root of e to the 2x. This is a VCE question. The diagram shows the graph of the function with domain R. What is the domain of the derivative function? Well, with these ones, it's best if we can sort of visualize what the domain is and then see if we can match it up with one of the answers. It looks to me as though the derivative would be defined for all these negative values of x, so from negative infinity at this -3 here, because it's smooth, it's differentiable at that point. You keep coming down, at 0, we've got a sharp point, so that means it's not differentiable there. All along from 0 to 3, not inclusive, it looks like it's differentiable, and from 3 onwards, not inclusive, it's differentiable. Alright, let's see, so negative infinity to 0, that works, but we're not including the point 0, so it can't be that, because that's a square bracket, it can't be a. It is going to be all real numbers, but we can't differentiate it here, and we can't differentiate it here, so it's all real numbers, not including 0 and 3. So let's see. This next one here, which of the following is a possible derivative function of the following graph? Well, it looks to me as though we've got some sort of cubic that's been put on its side, so maybe something like x to the power of 1/3. Okay, let's think about what's the gradient here. When x values are large and negative, it's got a shallow gradient, and then it starts to increase, as we can see here. It starts to increase, and then when we get to the middle, well, what would we draw here? We'll draw a vertical tangent, but a vertical tangent has a undefined gradient, so we know that on our graph we can't have a derivative function defined at x equals 0. Okay, so it can't be a because our derivative would be defined at that point. That leaves b, c, and d. Well, x values are large and negative, we have a small gradient, so that this here seems to be a possible option, because when x values in it, we've got a small gradient, and as the x values get closer to 0, we get larger gradient, so that seems like a possible option. And the same applies on the other side here. When we have large positive values, we have large positive x values, we have a small gradient, so that seems to follow. Let's see, why can't it be these other ones? It can't be this because this derivative function is defined at x equals 0, and it can't be this because it can't be d because it doesn't match up with the gradient. It's positive gradient throughout this whole thing. If this was the gradient function, we'd have negative gradient values here, which we can't have. So it's B. Question 4, a function is not differentiable at x equals a if the graph of the function is, we know if a function is not continuous at x equals a. We know that that's a possible option. We know that that is an option. So if it's not continuous at x equals a, it's not differentiable. If it has a cusp, so if it has something like this, it's not differentiable at that point, so that seems correct. It has a horizontal tangent at x equals a. Alright, well how would we get a horizontal tangent? Maybe we have something like that. It goes like that. Well, that would just be a gradient of 0. So that would be differentiable if it has a horizontal tangent at x equals a. It has a vertical tangent at x equals a. Well, let's draw something that would have a vertical tangent, maybe something like this. Vertical tangent means it's not differentiable at that point. So 1, 2, and 4 should be our answers. So that's C. The limit as x approaches 1 of x squared minus 1 on x minus 1. The key thing to remember here is that when we're taking the limit, it doesn't necessarily mean that we're just substituting in the value of 1. We are allowed to manipulate things so that we can see what the value is when we approach that number. If we think about difference of perfect squares here, because we've got x squared, which is a perfect square, and 1 is a perfect square, and it's the difference because it's the subtraction. So we can write this as x plus 1, x minus 1, all divided by x minus 1. Okay, so that cancels with that, and we're just left with the limit as x approaches 1 of x plus 1. 1 plus 1 is 2, so that's B. On to the short answer. Find the derivative of f of x equals 1 on x squared. I'll write it out because you can't really see it. Using first principles. Alright, first principle says the limit h approaches 0 of f of x plus h minus f of x all divided by h. Okay, applying that formula gives us the limit h approaches 0 of 1 on x squared. So that's 1 on x plus h squared minus 1 on x squared. All divided by h. Alright, with these sorts of questions we have to get a common denominator in the numerator here. So that means this x squared needs to be multiplied on top and on the bottom here. And this x plus h all squared needs to be multiplied on the top and the bottom there. So let's do that. So it's the limit. So h approaches 0 of, okay, so it's x squared on x squared times x plus h squared minus, alright, x plus h all squared on top of the other one. So it's x plus h all squared on x squared all divided by h. Alright, now we can put them together because we have common denominators. So it's x squared minus x plus h squared all divided by, oops, I forgot this part here, x plus h squared. So they have common denominators, so it's x squared, x plus h squared, all divided by h. Alright, we keep going, we can expand the top part, so that's the limit. So h approaches 0 of x squared. Alright, expanding this out would give us minus, let's just do big brackets for now, so to be x plus h, because that's what squared means, all divided by x squared by x plus h squared. That's not really a necessary step, but I'm just doing it so you can see what you have to do. Minus, alright, first x squared outer plus hx inner, and last would be plus h squared. Undoubtedly someone will forget this minus, so just be careful there. all divided by x squared times x plus h all squared all divided by h. Running out of space. Let's see how we can go here. So it's the limit. Well, what we can say this x squared is going to cancel with that x squared. This hx will become 2hx, and then be h squared on top. So it's going to be the limit as h approaches 0 of 2hx plus h squared all divided by x squared times x plus h squared all divided by h. We're going to have to squeeze it up here. Okay, it looks like we can take h out as a factor. So we can take h out as a factor at the top, so it's 2x plus h, all divided by, well, dividing by h at the bottom, at the very bottom, over here, is the same as multiplying by 1 on h, so that h can go into the denominator. So it's hx squared by x plus h squared. Those h's can cancel out, so we get 2x plus h. I forgot to write the limit, as I do. The lim as h approaches 0. Lim as h approaches 0 now, what we have is 2x plus h, all divided by x squared times x plus h squared. Alright, now as h approaches 0, this term will tend towards 0, and this term will become x squared. Hopefully you can see that. So if this h goes to 0, we're just left with x squared there. So f dash x is equal to 2x on, well, we're going to have x squared times x squared, which is going to be x to the power of 4. Which gives us 2 on x cubed. Now, I've made a mistake, and I even mentioned it before. This minus, I didn't multiply it in, so that minus needs to go in there, and there, and there. So along the way, this should have been minus 2x minus h. Anyway, take my word for it that if you just redo that, you would get minus 2 on x cubed. That was it. Next part, find the derivative of this. Well, it looks like chain rule to me, so we're going to say u equals 3x to the power of 4. The u dx equals 12x cubed. Y equals cos of u. And dy du equals, derivative of cos is negative sign. So negative sign of u. Okay, so therefore our answer is, using the chain rule, dy dx equals dy du times du dx. That's going to give us negative, so it's going to give 12x cubed. So it's this times this. And this negative, I'm going to bring it at the front here. So it's going to be negative 12x cubed times sine of 3x to the power of 4, which was just our u term. Hence or otherwise, find f dash of pi. Okay, so f dash of x is that. So f dash of pi, well, it's going to be negative 12 times pi cubed. Wherever we see an x, we substitute in a pi, times sine of 3 pi to the power of 4. Okay, so that's going to give us negative 12 pi cubed. We can leave it in exact form. Sine of times sine of 3 pi to the power of 4. And that's just what we're going to have to leave our answer as. curve with the equation y equals ax squared plus bx has a gradient of 3 at the point 2, negative 2. Find the values of a and b. So it has a gradient at the point, gradient of 3 at the point 2, negative 2. So first thing we're going to need to do, since we're talking about gradients, we're going to need to find the derivative. So f dash x, or y dash in this case, if you prefer. So y dash is equal to 2ax plus b. Okay, has a gradient of 3 at the point 2, negative 2. So when my x value is 2, the gradient is 3. So what that means is I can rewrite this and I can say 3, so the gradient, y dash, is equal to 2 times a times x, or an x value of 2, plus b. Simplifying that down a bit gives us 3 equals 4a plus b. And that's going to be equation 1, because it looks like we're going to have to do simultaneous equations. And the other equation we can get is just from the original function. And the original function has a point 2, negative 2. So that means my y value is negative 2 in my original function when x is 2. So a times 2 squared plus b times 2. Simplifying that down gives us negative 2 equals 4a plus 2b. And that's our second equation. I prefer substitution usually, so I'm going to use substitution. So I'm going to rearrange 1. I'm going to rearrange 1 so that it looks like this. So it's going to be b equals 3 minus 4a. Good. And then I'm going to substitute that into 2. So now I'm going to substitute this b of 3 minus 4a into number 2. So that's going to give us negative 2 equals 4 times a plus 2 times 3 minus 4a. Okay, now we can just solve this because we've only got a's. So negative 2 equals 4a plus 6 minus 8a. If we expand this in, it's minus 8a. Okay, 4a minus 8a is minus 4a, so it's minus 2 equals minus 4a plus 6. If we just keep squeezing this in, we subtract 6 from both sides, negative 2, so it's minus 8 equals minus 4a. Therefore, a equals negative 8 divided by negative 4 is 2. So there's one answer. All right, well, if a equals 2, then b, we can just sub that into one of these equations. So we're just going to sub that a back in. So sub a in. And it gives us, I'll sub it into equation 1 just because I can. So 3 equals 4 times 2 plus b. So 3 equals 8 plus b. Therefore, b is 3 minus 8. If we subtract 8 from both sides, 3 minus 8 is negative 5. So there's our two answers. Find the coordinates of the point where the gradient is 0. Okay, that should be straightforward enough. We just have to let the derivative equal 0. So I'll just rewrite the derivative so we're clear. 2ax plus b. Okay, we need to let the derivative equal 0. Well, we know the a values and the b values as well now. So it's 2 times 2x plus b, which is negative 5. So that needs to be plus b. Plusing minus 5 is the same thing as subtracting 5. So that gives us 4x minus 5. Alright, let's solve for x now to give us the x coordinate. So that's going to be 5 equals 4x. X equals 5 on 4. Alright. Now we sub this x value back into the original equation. So we sub that back into the original equation. The original equation was y equals ax squared plus bx. Alright, with with the information we know about a and b, we can say it's 2x squared minus 5x. So we know y. Yep, so y equals that. Right, and we know we want to know the y value, so we substitute in an x value of 514. Moving up here, all right, so that's 25 on 16, so it's 2 times 25 on 16 minus 5. Let's just simplify that. So minus 5 times 5 is minus 25 on 4. So that would give us, the 2 gets multiplied, so it's 50 on 16 minus 25 on 4. Simplifying that gives us, we can make common denominators. I need to multiply the bottom by 4, so it's 50 on 16 minus 100 on 16. 50 is negative 50 on 16. We can half both of those, so it'll be negative 25 on 8. And that will be our answer. I don't think that can be simplified anymore. So our final solution is coordinates where the gradient is 0 is, well, the x value is 5 on 4 and the y value is negative 25 on 8. Okay, so this question says, for the function with the rule f of x equals x squared plus 2x plus 1, where x is greater than or equal to 0, and x plus 1 where x is less than 0. Okay, when I look at something like this, what I'm thinking is there's two possibilities. Well, there's only one possibility for what it actually looks like, but in terms of the question, find f dash x and state the values for which it exists, all I'm really concerned about is what it sort of looks like. So it could be disjointed. So this is linear. So the first part's linear up to here, and the second part's quadratic. So it could look something like that. And the quadratic is inclusive of 0, and the linear one is exclusive. Or it could look something like this. So they're not connected in that version, or maybe they are connected. So maybe they look something like this. So this one's open circle, but maybe they touch each other. So then this one, then the quadratic touches it. Either way, in this option, it's not continuous. In this option, it's not differentiable at this point because it would be a sharp point. So having an understanding of what the original function looked like is really going to make your life easier when you have to do the derivative function. So if we do the derivative function now, we can do it just like we would take any normal derivative, and then we just got to be careful about certain points on the graph for where it's differentiable and where it's not, and how we're going to include those. So the first part's going to be 2x plus 2. Second part's going to be 1. Okay, now the hard part is to think about the domain. So if this part says that x squared plus 2x plus 1 if x is greater than or equal to 0. Well, if x is greater than or equal to 0, we know that it's not going to be differentiable at the point x equals 0, because whether it's a sharp point or whether it's not a sharp point, we can't differentiate at endpoints. So this one is now going to have to be exclusive of 0. It's not going to include 0. And the other one is also still not going to include 0, so that one's going to stay the same like that. When we draw the diagram, hopefully it makes a bit more sense. So the first part is x, sorry, the second part, we'll start with that. It's x equals 1, sorry, y equals 1 when x is less than 0. And it's not inclusive, so it's something like that. And that's the point 0, 1 there. Okay, and the next part is 2x plus 2. Okay, so the 2, it means it's got a y-intercept of 2, and it's not including, so it's going to be like that. And this is not going to be very to scale, but rise over run has to rise 2 for every 1 it goes across, so it's going to have to be up like that. And for all values of x greater than 0. So that should be our final answer there. And just to be clear, that's the line 2x plus 2. And this is the line 1. F dash x equals 1, just so we're clear. F dash x equals 2x plus 2. And that's our answer. Last question. Sketch the graph of f dash x on the axis below. Not all points can be determined. All right. This is our function. Looks like some sort of cubic. We know at the turning points of any function that the gradient is 0 because we draw a horizontal tangent. So maybe there somewhere. That means we're going to have on the gradient function, we're going to have a y-intercept. Similarly down here, it means we're going to have an x-intercept, if I said y-intercept before, an x-intercept wherever the gradient of the previous function is 0. So then we have to think about what happens before that. So when my x values are less than this point, well, all these values have a positive gradient. If we think of the slope of the tangent, they're positive gradient, but they're getting less steep as we get to 0. Because it's really steep down here, and it gets less steep as we get closer to 0. So that means it needs to be coming from positive values. So it needs to be coming from down up there, gets to 0, and then from the turning point, then it starts to get negative. So sort of small negative, and then when we get to the middle here somewhere, it gets to the maximum negativeness, and then it starts to increase again. So that means around this point here, we're going to have a minimum. So it's going to come down like this. And because we know when we differentiate a cubic, it becomes the one order less, so x cubed becomes x squared. It makes sense that our answer looks something like a quadratic. And this is obviously just a sketch. We don't have any exact points. But there you go, that's the answers.